All right. All right, let's get started. All right, good afternoon. Just a few bits about organization. On the 6th December, we'll have a guest lecture on unsupervised learning for 3D, which will be from Professor Vidaldi from the University of Oxford. We will be using Zoom for that. I'll probably be here and stream it, but you can also just stay at home for that. Also, I'm asking you to be, in turn, here in person for the lecture on the 13th December, where my teaching will be recorded for my teaching course. All right, then thanks for providing the midway feedback. We got a couple of feedbacks, a lot of useful feedback as well. I sort of giving a summary on the right-hand side of the qualitative points. One of the things we're already implementing is we're trying to keep the third assignment a lot lighter. So we're re-editing what we wanted to do in the third assignment to make it easier. For the schedule, yeah, there's not much we can do. We realize this is quite tough, and we'll try to accommodate this, especially in the tutorials and work colleges after the lectures. So Philip will probably be taking a bit more like a recap and like hopefully a bit slower, but there's also a bunch of stuff we need to go through, so it's a bit tough. Some people mentioned they would like to see more depth. Well, I think last lecture was hopefully pretty in-depth into graph neural networks and equivariances. And so are today's and Friday's lecture as well. So we're hopefully the people that mentioned these points will be satisfied with that as well. And yeah, many more individual points. And yeah, keep it going even if the next feedback will be basically after the exam, which is like this written feedback. But even before that, like keep the feedback going, and we can see that you're active on Piazza, which is also great. And with that, we'll jump into today's lecture. We'll be covering a lot of stuff, and the main aspect we'll be covering is generative modeling. And within that, we'll be talking about autoencoders, latent variable models, and then finally we'll arrive at the famous variational autoencoder, which was also invented here at the University of Amsterdam. So let's start with the question, what even is generative modeling? So in machine learning, we often talk about discriminative versus generative modeling, and the difference is sort of shown at the bottom. So a discriminative model only cares about, is it A or B? Is it the cat class or the dog class? While generative modeling cares about modeling the individual data points. So you could say one is about getting the output of a certain label, conditional on some inputs. That's py given x. And the other one is sort of saying generally how likely is this sort of data point to be existing in the world. And p is some sort of probability density function where a high value would mean x is likely. And we'll be formalizing this a lot more later. But probability functions also means that it's normalized, right? Probabilities means if you sum all the possible things, you will end up at 1. And this will be really the thing that will haunt us a bit this lecture, that if you want probabilities, we need to normalize, and often this normalization procedure is not that easy. But before that, let's keep going. Why generative modeling? So typically, a discriminative model normalizes the outputs in terms of classes, right? So we run, for example, a softmax. So for these two images, you get probability of cat being 70% and dog 30%, for example, and the opposite for the dog image. However, if you then take this cat-dog classifier and apply it to like a picture of an ape, it might still give you something like 40% cat, 40% dog and 60% cat, or something which isn't all that meaningful. And it gets even worse if you give it some sort of meaningless image, and it still thinks, oh, it's somewhere, it's one of those classes essentially. And generative modeling is sort of the idea that this can cure it, because if you do generative models, the probability is normalized for inputs. So yeah, it will see plenty of cat and dog images, maybe not so much images of apes, but this sort of weird abstract image is probably not in the distribution of photographs or in the distribution of training images, so it will have a very low probability value. So this is the idea of generative modeling put in pictures. There's another reason why generative modeling is pretty cool. It is essentially what every other discipline is doing for a good reason. So for example, in physics, we model the planet motions using some sort of physical laws. In economics, we, for example, say a household has an income and has labor, and you combine these two, and then a company has labor and capital, and with that produces something else, and all in all, you sum these things up, and then you have the state of the economy, for example. Similar for other disciplines of applied mathematics, biology, or geology. And the benefits are countless, really, at least for these disciplines. So first of all, it makes your model or whatever you're doing pretty interpretable because you're explicitly modeling what is happening. It also makes it testable because now you can build your model and then compare it against the real data, which is great. And especially if your model is kept simple and then it fits the real data, it's pretty good. It's probably as good as it can get, with, of course, some trade-off between complexity of the model and how good it can, for example, be used as predictive measures. As I said, if you can sort of take those unnatural outputs out, it can also help with making discriminative models more robust. And finally, it might be also quite similar to the way how we, in our brains, model the world. So in the brain, we often have something like predictive coding, where we sort of anticipate what's going to happen next. And if that doesn't happen, then we actually perceive something as being different. So generative modeling is quite important. And with Bayes' rule, if we see, for example, all the way to the right-hand side in violet, you can see this unconditional probability distribution, P of x. X could be time series, could be any sort of signal. For now, we'll be looking at images because it's on the one hand, pretty complex data, very high dimensional. On the other hand, it's pretty abundant. So that's why people typically experiment with images for that matter. You can see the discriminative model we had earlier, and then the prior over labels is something simple, like if you have cipher 10, it's just 1 over 10, because it's a balanced data set, for example. So the prior over label can be extremely simple. And if you simply combine these two elements essentially together, you already get a conditional generative model. So you get it for free, thanks to Bayes' rule. So yeah, previously we focused on this conditional distribution, conditional output. Today we'll be focusing on learning parameters such that we can get the probability of an input point. And if the true distribution is P star of x, for example, the true distribution, of course, we would never know. It's a distribution which generated, for example, the real images. Our goal for today will be learning a set of parameters such that this modeled distribution will be very close to the real distribution. And we're not the first to do that. In fact, this sort of approach has a huge history in machine learning, as you will be seeing today. There's a bunch of approaches which have been used. The important distinctions are explicit density versus implicit density. In explicit density models, you can explicitly compute this P of x. So it means you can literally get a number that's between 0 and 1 for an x. For implicit models, you cannot get this number, but you can actually sample from this distribution. So this is what we'll be doing on Friday with generative adversarial networks, which can give you nice images, but you don't have any idea about how likely something is. Today we'll be talking about the variational autoencoders or variational density methods, which basically approximate this explicit density. So it won't be giving you exactly P of x, but something that's an approximation to it. In fact, something that's a lower bound to it. All right, so this is the name of the game for today. And we'll start with autoencoders. What are autoencoders? So auto means self, and encoder means simply going from one thing to another thing. So below you can see the picture of what an autoencoder does. It takes an input, let's say an image x, and reconstructs the input. So that's fairly trivial. In the middle, you have something called the bottleneck layer, which has fewer dimensions than the input. And yeah, the output simply reconstructs that. And it's being used to, or it is used for learning efficient encoding or embeddings of unlabeled data. Because as you can see, there's no mention of any labels here, so it's an unsupervised learning technique. Oh yeah, and you can see here the shape of the latent representation is also typically that you go from image being like certain size, and then you gradually decrease the spatial dimensionality, and then you increase it again using, for example, the transposed convolutions that we've had in the convolutional neural networks lecture. All right, the structure looks as follows. It has we call the first part the encoder, the second part the decoder. We go from typically X to a lower dimensional latent space, and then from this lower dimensional latent space, which we can call the features you get Z, we're going to map back to the observation space X. And it could be literally anything. If you wanted to, you can implement an autoencoder only with fully connected layers, with one-by-one convolutions. It wouldn't really matter. Typically, it's convolutions, though. And typically, it's trained with something like an L2 loss, which is simply applied per pixel. There's better losses, because per pixel L2 loss ends up giving you pretty blurry predictions quite often. But importantly, well, you need to remember here is it doesn't use any labels, which is pretty great. The question is why autoencoders, right? Who invented this? Why did they need to do that? Because you don't need to wait for hours on some compute cluster just to compute an identity function, right? Like if all you wanted to get is a blurry output of the two, you can literally just apply a blur operation on this image. So clearly, the output isn't really the specialty here, what we need. The key to understanding why autoencoders are important is this bottleneck. This bottleneck is of lower dimension than the input size. So what this means is if the autoencoder is to reconstruct the output in a good manner, it needs to compress information. And compressing information means keeping all the stuff that's important, and stuff like noise, like raw pixels, which were maybe falsely encoded, or stuff like that will be discarded. So the lower dimensional representation will keep only the important parts. And just in case for those wondering why this is called a bottleneck, usually bottles at the top are more narrow, so kind of like this, except that here, this is not a very useful bottleneck. All right, so I said the key is the bottleneck, and this bottleneck now has a very compressed representation. So these lower dimensional feature representations can now be used for various things, like downstream evaluations. You can now put an image through it, and it should capture all the important information. This bottleneck layer encourages this, and compression is very related to learning. For example, if you can write down everything we've learned on this course on a post-it, then it means probably you've understood the course very well. And there's some more sophisticated literature that relates compression to learning. And it also removes the redundant information from the raw output. For example, if you think of digits, if you see at the top middle a half-sized loop, you pretty much know how the bottom half is going to look like, because within the digits, only the 8 has this sort of very distinct shape, right? Or the 9 would be slightly to the right and stuff like that. So it removes this sort of redundant information. It only keeps the important information that you can then use to reconstruct the output. Yeah, and this is what the reconstruction loss does. And so autoencoders with neural networks have been around already in 2006. And here what you see is the outputs of the Z layer, so a two-dimensional layer. So the bottleneck is just two-dimensional, and you encode a bunch of points there. And in this case, you're encoding digits from 0 to 9. And you can see if you simply use PCA, some of these digits are overlapping, which is not very nice. But if you use an autoencoder, which is basically a very nonlinear PCA, then each data point or each ground truth label, which is indicated by the color, is sort of nicely spread out the way it should be. Fun fact about this one is actually that here the autoencoder, the encoder part has the same weights as the decoder part, except that they are transposed such that they get smaller going from one side and get bigger while going from the other side. But normal autoencoders don't have this sharing of the weights typically. You can also use this middle representation as some sort of hash function because it costs a lot less space, but still gives you a pretty unique footprint of the input ID. Autoencoders since then have improved by quite a bit, and this one says big BiGAN, so it's already a generative adversarial network, which we'll be talking more about in the next lecture. But essentially, it has this encoding part in there, so it's pretty much it's pretty much an autoencoder. And there's some table from their paper, and you can see this mentioned with a supervised logistic regression classifier, which is exactly what we talked about in lecture 6 about the linear probing evaluation protocol. Question? I'm sure there's works that use attention in autoencoders as well. Autoencoders per se are rarely used, I would say, nowadays. This is, as you can see, I mean, this is not big autoencoder, but big BiGAN. So the inspiration from autoencoders is still around, but there's not that many applications for autoencoders remaining. But everywhere where convolutions have been applied or MLPs have been applied, people have used attention. So you can be pretty sure that it exists, yeah. All right. So yeah, what they show here is that the encoder you learn for this autoencoding task is pretty general purpose and can be used for all kinds of other things. And the images you can generate from these are actually pretty good, at least from when looking from far away. If you zoom in, you sort of see these pretty nightmarish structures, which was basically the standard until we arrived at these diffusion models that we covered in the first lecture, and that we'll be also talking about a bit more in the next lecture as well. But this is sort of the typical quality you get. Now, the dimensionality of the latent space typically is crucial. If the latent space is too small, it's even too little to capture all the important information, right? So it cannot even capture the stuff that it needs to reconstruct. It's already amazing that it can do this sort of stuff with just 2D information, even though you have 10 different labels, right? But of course, the 2D space is continuous and not binary. And yeah, once you go to 5D, it looks pretty good. Once the dimensionality is too high, it will start keeping irrelevant information and tries to model all the noise, so it will overfit on the data set and not necessarily capture the stuff that you wanted it to capture. So at this point, a quick quiz. PCA is the motivating technique behind the first initial autoencoders. What is true about PCAs? They can have local optima and should be run multiple times. PCA can return more interpretable features. PCA generally yields the same results as linear regression, or 4, PCA generally struggles with outliers. And I know you've done PCA, I think, in ML1, but I mean, even without, have a think about it. All right. 3, 2, 1. So 2, 4, 4, 2, 5. 2, 4, 2, 4, 3, 2. All right, so yeah, 1 is not true. It's very deterministic. 2, generally not, because it returns a linear combination of features. So if you have a data set which has household income, square footage, whatever, it will just give you a linear combination of 0.3 times this minus 0.5 times that. So generally not more interpretable. You can make it more interpretable, though. 3 not true. Linear regression is a supervised thing, and PCA is unsupervised. There is, of course, a relation, but it's not that. And 4 is true. It struggles with outliers because PCA is essentially having a L2 loss for reconstruction, and L2 loss is very susceptible to outliers because outliers means they're far away, and so they push the whole distribution towards them, and so you get a big error for everything else. There's also, I posted a link to a really nice explanation of what PCA does here. It relates to wine, so if you have a minute, you can at some point take a read of this, which is quite interesting. All right. There have been, I mentioned, there have been some applications for autoencoders. One is the denoising autoencoder, which is a super simple idea. You simply add some noise to the input, then you train the autoencoder to reconstruct the original input, but without the noise. So what it does is it denoises. This is similar to this point about learning invariances to augmentations, right? You're essentially augmenting the input, but you're saying explicitly, oh, but the output shouldn't change. And again, for this, the features need to capture useful structure and need to learn how to remove the noise or ignore the noise, essentially. And you can use it actually for something like denoising old photographs or decorrupting data and stuff like that. On a manifold, or like on the picture, how it looks like this, on the image space, you get from this blurry looking picture, blurry is now the noise that we're adding, to a very sharp looking image. So what it essentially tries to do here, I should say, here the manifold, this sort of lower dimensional space, is simply depicted by a line. So remember this picture from a few lectures ago? This manifold was sort of this surface which was lying in 3D space. Here it's a line in 2D space. So basically once you blur the image is not really on this true manifold anymore. And then the model, what it does, it learns how to push it back to this true manifold, basically. And that's all the image model is trying to learn. Yeah, question?
So for example, in this, these example photographs that you took, would something this, I'd say that this is pretty decent, this is doing a pretty decent job. Would something like a general autoencoder, NLP style autoencoder work this well as well, or is there something else?
So these denoising, so the question is whether an autoencoder can do the same thing, I guess?
Well, like a very simple MLP auto. Like.
Oh, you mean whether it doesn't need to be convolutional, you mean? Yeah. Right. I would say it depends, right? Like convolutional definitely has a lot of benefits here, because an MLP by itself would be just at every location, and you cannot really tell every single location whether it's blurred or not, because blurring is some sort of spatial thing. So you definitely need some spatial context. Yeah, right. You can also imagine if it was like black and white noise, so you just zero out a pixel or not. If you simply only look at individual pixels, you wouldn't be able to tell. So you need some sort of CNN or convolutional-like architecture. Yep. And you need to train it whatever you do. Like if you're having 0-1 noise, then you need to train it like that. If you're having blurring noise, you need to train it like that. So it doesn't generally denoise, basically. All right. Another application has been sparse autoencoders. It's just a different way to make a bottleneck, which is quite interesting. So here you have the bottleneck is essentially what's called overcomplete, which has more hidden units than the input. And now you simply train it in a manner that induces this sparsity automatically. So for example, you apply L1 regularizations on the activation of the hidden layer, or you, for example, just keep the top K units. So even though, of course, like all the units in the hidden layer will be firing, you simply look at how strong are they being activated, and you only keep the top 5, top 10 or something. And that way you also have a bottleneck, but in a way you have a bottleneck that's being learned. And it's just another way to have this bottleneck. I've mentioned the applications a bit. One curious fact is that if you have linear autoencoders, you reconstruct what is PCA. And I've added the formula at the top, where you're simply learning V and W in PCA, essentially, and you have the squared loss over there. And autoencoders are interesting, or like just very important generally, because they have this generic principle of use what you have, right? We're not even using something like augmentation invariances. We're not using labels. We're simply using data. And we're using data, and we're learning a neural network based on that. So that's like a really, really generic principle. No need for augmentations or equivariances or anything like that. And we had some applications in denoising and some in representation learning. However, autoencoders are not probabilistic, so they're not generative models. They are looking like them, but they cannot generate new data points. And of course, so far we haven't even talked about probabilities, so they cannot tell you how probable one image is. So why can they not produce any new data points, right? So it's all about this bottleneck layer. These latent representations, they could be extremely entangled. So what does this mean? We have no way of knowing, for example, if the first dimension goes from minus 0.05 to 0.08, and the second one could be from 150 to 210 or something like that. But not only do we not know that part, but also we don't know how the different dimensions are related. So it could be that indeed it goes from 0.05 to 0.08, but whenever it's at 0.08, the fifth and the 21st dimension are very high. So we don't know about these correlations because we haven't modeled them at all. So this makes it really pretty much impossible to generate new data points from this vanilla autoencoder structure. So this is the problem that we are facing. So what we'll arrive at this lecture is basically the variational autoencoder which will solve these issues. The main idea is that you learn features Z from the data, just like before, and then you model the outputs via first sampling from this Z distribution, and then you get an output conditional on this Z. So if you multiply P of Z times P of X given Z, you arrive at P of X. And this P of Z is simply assumed to be a Gaussian distribution, so you're keeping that one as simple as possible. And that's sort of the rough guideline of where we'll be going. Before we go there, however, let's talk about some VAE use cases and the fact that they are still very much up to date. So the first DALI paper used a version of VAE called VQ-VAE for the image generation part. There's another paper which used VQ-VAE, or like a variant of that, for music generation. And yeah, it sounds pretty good. You can take a listen to it later. There's also a pretty interesting video that explains how it's being done. Yeah, all right. So now, are there any questions so far? All right, so let's dive into VAEs. So for VAEs, we need to understand latent variable models. So a latent variable model, depicted on the right, defines a distribution over observations by using some latent, which simply means unobserved variable Z. And in this case, in our case, we simply specify the prior distribution for this unobserved Z. We're just going to say it's Gaussian, which is the easiest thing we can do. And then this likelihood P of X given Z will be connecting this latent variable to the observation. So you go from Z to X with this probability distribution. I've colored in some parts, the prior, the likelihood, and the joint distribution, because these are sort of the words that we'll be using a lot. And what we'll be tackling is getting at this P of X via computing the posterior distribution P of Z given X. And also, on this note, I copy-pasted something from a nice tutorial paper. When something is called likelihood versus probability, because I'm also quite confused sometimes. And the main difference is for probability, for calling something a probability, you assume the hypothesis is fixed and the data are free to vary. And for calling something a likelihood, you assume the data is fixed, but the hypothesis can vary. Yeah. Just as a brief note, and maybe I'll be using them interchangeably at some point. Question?
So you mentioned we specify the prior distribution Pz for the latent variable, and we usually use the Gaussian distribution.
Mm-hmm.
I wouldn't see a way to justify if it is a Gaussian. Is this just like an assumption we make, or?
It's a good point. Hopefully this will become clearer in the later part, but the main gist why we can say that Z can be Gaussian distributed is because we assume this P that goes from Z to X to be very, very, very nonlinear. And so you can start off with anything. It could be a cubic uniform distribution. As long as we model it, switch it enough around, it will eventually become the real thing. So that's why. These arrows are in nowhere linear operations. Was there another question? No? All right. So we can think of latent variable models as essentially explaining the observation, and Z being the factors that explain the data. So to generate an observation from the model, typically we sample Z according to P of Z, and that's sort of what this tilde means. And then we sample X according to this other distribution. So what we have to do is something called inference. And in machine learning, inference is a word which describes the process of going from observations X to the latent variable Z. And we want to know the factors Z that generate the data. And a brief note here is that sometimes in machine learning and vision, we also say something like inference speed, but that typically refers to test time, so without gradients, without training, etc. And that's not what's meant here. So inference here is something, yeah, completely different. Brief reminder, here some notes from ML1 that you might have had. I know not everyone here has taken ML1, but yeah, latent variable models have been explained somewhat there, but we're going to go a bit deeper into that one. And we'll be talking about inference now. So inference is about computing the posterior distribution for a given X, which means this one. So you can see, so the first equation, the first equality is simply Bayes' rule. And then what happens next is, OK, you can write P of X simply as the integral over all possible Z dashes. And so these are simply identities. And so what this means is in order to compute the posterior, we need to solve the subproblem of computing the marginal likelihood of the observation, which is this one. So we need to be able to solve this integral. However, this is usually not easily done. And that's why we have the variant of variational autoencoders, because this integral goes over Z. And I said Z, OK, we can model Z as being a Gaussian, but it's still a Gaussian in a d-dimensional space is still huge. In fact, later I'll have some calculation on how large it is. And we can actually see inverse, or inference actually is the inverse process of data generation. So given that, we can generate these pairs of X and Z in two ways. So there's this one way that we just mentioned, first sample Z, then sample X. But what's completely equivalent is first sample X from this P of X, and then compute Z from this distribution. So the joint distribution of these pairs is exactly the same because of Bayes' rule. So no matter how you do it, you arrive at the same equation as shown at the bottom. And actually what we'll be doing is we'll be using the right identities to be conducting inference. And before we do that, just a quick reminder of why should we even do inference. We said that getting a Z that explains the data is the important part. And we want to infer the posterior distribution for data point in order to know what kind of configuration of variable set might have possibly generated these. And then once we know that, we can generate new data points. And it allows us to learn this generative model because now, yeah, we need to figure out how these latent variables are done. So let's talk about how we do it. The normal way, the typical thing would be to do it with maximum likelihood. What is maximum likelihood? It's sort of the dominant principle in ML. If you have a probabilistic model, you want the one that has some free parameters. You want to choose the parameters that have most likely contributed to the data that you observe. So more formally, given a set of data points, we define a model to represent the data and find the theta that maximizes the probability of the data under the model. So it simply looks like this. Right? You have n data points, and you simply sum up the log probabilities. You can see that as sort of your loss function, essentially. And whenever this loss function has the highest value, that's your right choice of parameters. However, for latent variable models, you don't have any closed form solution. And just as a brief note, why the logarithms? Here's some very quick reminder of why we arrive at logarithm. For example, if we simply assume every data point is independent, the probability of a whole data set is simply the multiplication of all those probabilities. If you have a multiplication of products, you can simply use the fact that the logarithm is convex, so you can replace that, and the product of that you can turn into a sum, and in the end you will arrive at this form. And you can replace this, or what we'll be doing is replacing this probability with a function f with parameters theta, which we will be learning. So this maximum likelihood, I already mentioned for latent variable models, this isn't solvable. But let's take a look at the gradient of such a maximum likelihood estimation. Right, so it's an equation, a bunch of equations. It isn't that tricky, though. So the first equation is the identity that we have from the right-hand side, which is simple mathematics, basically the chain rule for the logarithm. The second equality is the simple change of the integral and the derivative, since the integral does not depend on theta. So that's the second equation. And the second row then uses that identity again with p of x and z. And finally, in the third row, we're simply rewriting the first term and the denominator using Bayes' rule. So it turns out from maximum likelihood, we need to compute the posterior distribution, which is this p theta of z given x. So that's what we need in order to arrive at a maximum likelihood estimation. And this is called, well, this will be the inference task, but this is difficult because of this integral. So we need to compute these high-dimensional integrals, and here's the computation that I've mentioned already. So for a three-dimensional binary z, this would mean iterating over all these possible things. But already for, let's say, 20 dimensions and binary variables, this would be 2 to the 20 possible images. And you need to solve this integral, or you need to sum up all of these 1 million sums. That's just for a single image and just for binary ones. But binary is very limiting, and we wouldn't be using binary to model any of this. Question? It's from this identity that's on the right-hand side. Yeah. Okay? Yes. All right, cool. Oh, yeah. All right. So, okay. So let's take a deep breath. Where are we? So we said autoencoders, nice idea, but doesn't give us probabilities. Idea one, let's model it with latent variables, where we go from z to observations x. If we simply fix p of z in some manner, p of x can be computed as this likelihood times the prior, which is nice. However, how do we get to that? How do we do inference, where we go from observations to model parameters? Which set was used for a given x? That's the thing we want to solve with inference. And we're stuck with this, or we arrive at this point where this normalize across data, well, in Z space, integral is intractable to compute. So the plan is to use variational inference, which is a common technique in machine learning to solve intractable integrals. And what this will do is it will turn this inference problem into an optimization problem. And optimization we know, and we've done a bunch as deep learners, so we'll feel more confident about that one. Yes?
Can you just go back one slide? I just realized I'm confused about what exactly are the model parameters? Are they parameterizing conditional distribution?
Where? Which row is that? Sorry?
So you have, how do we do inference, going from observations to model parameters?
Yeah.
What exactly are the parameters that we're after here? Like, which distribution do they belong to?
It will be about how you can get this P of Z given X. And we haven't talked about anything like model or parameters yet, but it will be a neural network, essentially.
Okay, and it will be chasing PZ given X.
Yes. Yes, exactly. Yeah, so all of these, except when I talk about true P of X, all of these P's basically have theta inside, except for P of Z. That one, well, depends. Well, yeah, just think of it as all of them having some parameters associated. And we'll be adding the parameters once we talk about how to optimize it. All right, so there's two ways of doing inference, or something that resembles inference. So one is Markov chain Monte Carlo, which we're not going to talk about today. It was, I think 3 years ago, it was actually in the Deep Learning 1 course. But it's not very complicated, but it's not very efficient. And that's why it's not being used here, actually. It has plenty of other applications, most notably in physics simulations. What we'll be talking about here is variational inference, which will approximate this posterior with some more easily computable distribution. So we'll be doing this trick of approximating something. Just a brief reminder or revisit. What we'll be using extensively is something called the Kullback-Leibler divergence. And it's a measure of how far two distributions are apart. So think of Q and P as some probability distributions. And then the KL, which is written in this brackets Q and then double pipe and then P manner, is simply given as the expectations over Q of log Q divided by P. And you can also write it as a sum. You can find the corresponding version on Wikipedia, for example, how to write it as a sum if you have discrete events. And the KL divergence has the properties that it's not negative, non-negative. It's only 0 if the two probability distributions are equal. And generally, it's not symmetric. So for example, if you have a fixed blue distribution P, and you're trying to fit Q, but you limit Q to be some sort of Gaussian, so it cannot really model these two peaks because it's just a Gaussian. If you do the normal KL divergence, it will sort of do the thing on the left. It will sort of try to fit both of these peaks. If you reverse it, if you use the reverse KL, it will do something different, just to tell you that actually KL is not symmetric, and it really matters which direction you use it. Another tool we'll be using is Jensen's inequality, fancy word for something really easy, which says that the negative logarithm, or the logarithm, is essentially a convex function. So basically, a line that connects two points will always be below the function. But you can use this and translate it to probabilities, which means what you can see here. You can take the expectation outside of the function if you're talking about logarithms. Just something that we'll be using. Another thing, we won't be using Markov chain Monte Carlo, but we'll be using something from Monte Carlo methods, which is simply the fact that you can approximate stuff by simply taking samples from it. Here's a quick recipe for computing the number pi without having access to it, simply by using Monte Carlo estimates. And the generic principle of Monte Carlo methods is that you can approximate integrals by simply computing an average. And via the law of large numbers, you get at the right estimates. And this, yeah, you can simply sample from a distribution and sum them up instead of explicitly computing the integral. And the hope is that if you sample, infinity times that, you will actually arrive at the correct output. And you can stop a bit shorter of infinity. In fact, we'll be using 1 or 2. and you will still get a decent estimate. Right. With these two tools, let's talk about variational inference. So the goal is to approximate this exact posterior with a variational posterior. And this will turn the inference into an optimization problem. And we approximate this variational posterior with variational parameters, yeah, and we optimize these. So now we're starting to introduce some parameters, and we will use a Kullback-Leibler divergence. And yeah, don't worry about the difficult-sounding names of variational and Kullback-Leibler and all of that stuff. So for the variational inference, so I said we can use this variational posterior, which is some sort of a distribution that we will use to approximate the real one. We can literally use any sort of distribution. Typically, we use very simple ones like Gaussian or uniform distributions and stuff like that. And the important thing is really only that we can sample from it, and then later on we'll be talking about how we can take gradients from it with regards to these the parameters that sort of describe this distribution, which we'll be calling phi, which are variational parameters. All right, so training with variational inference. So the question is what we do if the training, what kind of training objective can we use if the marginal log likelihood is intractable. So that's this one that we wanted to do. In fact, what we'll be doing is that the variational posterior will give us a lower bound on this measure. And if you want to maximize something and you're maximizing a lower bound to it, you will eventually maximize the right thing. So if we were to arrive at the upper bound, it wouldn't help us much if we increase that one. But since we're optimizing a lower bound, we'll be optimizing a lower bound on something that we want to maximize. That's good. And variational inference will be giving us that, and we'll be now splitting it into model parameters theta and variational parameters phi. All right, so how do we arrive at the variational lower bound? This is kind of the key. So we said this max, or this log p theta of x is not computable. So how can we arrive at the lower bound? The next best thing, basically. So first of all, on the left-hand side, we have the thing that we wish to compute. We can simply write that in a different manner by marginalizing the z and then simply adding it up across all of the z. So nothing magical happened here. The next thing is something weird. We simply multiply it by 1, right? You can see this q phi of z appear on both of these in the numerator and the denominator. All right, easy enough. Next thing is we use Jensen's inequality. And what you'll be seeing here, what happened here is simply the logarithm went inside. Also not a big deal. And in the last one, instead of the integral of over all z multiplied by q, we can simply write it as an expectations over samples from q. Right. So instead of having this generic integral, you can simply, that's multiplied with this q factor, you can simply instead sample directly from q, and then you have this expectation. And this is the variational lower bound. So therefore, for any such q phi of z, we have now approximated our target variable, or target loss function, however you want to call it, with this lower bound. And now we can maximize this one, which has both parameters theta and phi, with regard instead of this log p of x. Right. So this variational lower bound. Right. So yeah, we haven't made any assumptions about this q of z. In fact, we can actually write it as q of z given x. Since, remember, it came from simply multiplying by 1. And this thing, written like that is called the evidence lower bound. It's essentially the same thing, so you can call it variational lower bound or evidence lower bound. And this is the simplest and most widely used ones of the variational lower bounds. And the good thing about this one is, the same one on the previous slide, is a higher elbow means a smaller difference to the true probability distribution, which means you have better latent representations. And a higher elbow also means that the gap to the log likelihood tightens, right? If you get higher, you will get closer to the real thing, so you will have a better density model. This one we're going to skip. You can actually write it in a different way. And if you write it in a different way, what you will arrive at is actually that the elbow, which is the first thing on the left-hand side of the equation, is given as something explicitly. So you don't have this inequality. And so writing it out like that, you can see that the elbow is essentially the likelihood of the data and the latents plus the entropy of the distribution of the latents. So regarding entropy, and also, by the way, all of this essentially will be explained a bit in more detail as well in the assignment as well. So I highly recommend, if you're not intending to complete it, but at least like read it through, that will be very informative, I think. And of course, like coding it up will be the ultimate, as always, the ultimate experience of understanding something. But the interpretation here is pretty nice, because now you can see that this elbow has two components. Well, first we increase the likelihood of that this latent goes along with this data point. But we also try to not have this latent distribution collapse into anything, such that Z is not like a function that only has one value, because that would be very low entropy. So high entropy means it's nicely spread across. And again, with this other rewriting that I've mentioned, you can actually rewrite the elbow as follows, which I'm, so I can walk you through it, but maybe it's not super important. But it basically uses the fact that the log of A divided by B is simply the log of A minus B. You can see that in the last equation. And in the first equality, you have the decomposition of the joint probability into the multiplication of two terms. So going from the first equality to the second one in the first row still, you simply use Bayes' rule. Next row, you simply use the fact that the logarithm of A divided by B is log A minus B. And finally, we recognize the first term is simply the log likelihood that we've talked about all the time. Because there's no dependency in Z, we can simply write it like that. And the second term is the Kullback-Leibler divergence. So writing it out like that, we've arrived at this. So this means our elbow is equivalent to minimizing this gap, right? This gap is exactly what stands between what we really wish to approximate versus what we're actually approximating. And yeah, so if you take the gradient of this thing with regards to phi, you will get the thing that this is the only thing that we're optimizing, right? Because the first term doesn't have any dependency on phi. And this gap, we're essentially, well, if we're optimizing the elbow with regards to phi, we're minimizing this Kullback-Leibler divergence, which is funny because both of these terms, the left and the Kullback-Leibler divergence, are not even computable. However, we can compute the difference between these two intractable quantities, and not only we can compute it, but we can actually optimize it. So this is kind of, with only this magical thing of lower bounding something, we can sort of do something that's quite magical. So how does it work now that we have this lower bound? So if we want to train the model parameters theta with regards to the elbow, we have these nice two potential options. Either the likelihood of x will increase or the gap will decrease. So then the idea is, okay, we want to model it as well as possible, so we need a very expressive variational posterior so that we can decrease this gap as much as possible. So now the question is, how can we choose this variational posterior? And I'll give you this another breather slide, and then we can take a break. So this stuff we just had in gray. And so now what did we do? So we used another probability distribution and Jensen's inequality to arrive at the lower bound on the quantity that we wanted to optimize. This lower bound we called elbow, and it's given by this equation, which is the difference of two quantities that we can actually not even compute. We also quantified the gap of elbow to be this KL divergence, and if we optimize with variational parameters, this is the only thing that's going to change. So now the question is how to choose and how to optimize Q. And with that, let's have a 10-minute break. So let's be back at 5 past. All right, let's continue. We're going to continue now. All right, let's think about what the form of the variational posterior might be. So the default choice we'll usually go for is a fully factorized distribution. In classic variational inference, and again, you need to remember that this sort of techniques have been around in machine learning way before deep learning, and is also related to some techniques they do in physics. And this is called the mean field approximation, and this field already reminds you a bit of physics. And the high-level idea now, the high-level idea, which I'll give briefly here, is what we're trying to do. Instead of modeling, for example, each pixel independently, so the probability of an image X would be like the multiplied probabilities of all the individual pixels, which doesn't make sense, right? Because the pixels are highly correlated. What we're doing instead here is we're modeling high-level latent factors that can capture these independent factors. For example, object type, background, camera angle, lighting, etc., such that we can get the probability by simply multiplying these independent factors together. And these independent factors, or in this case, sorry, that are such that for every pixel, you only need to have this Z. And in fact, we'll be dividing this Z furthermore into individual ZIs to factorize it and such that we can have a multidimensional Z. And there's a couple of options for this set now. We can have mixture distributions or Gaussians, autoregressive ones, which actually capture this dependency between pixels, for example, or flow-based models. Typically, there's a trade-off between training speed and how good they are. What we'll be doing is simply Gaussians with a diagonal matrix. All right. So what we'll now need to remember is that the posterior distribution, P of Z of X, is different for each observation, right? So whatever you have as an input image X, the outcoming Z is different. So in traditional inference, you would have to do optimization to arrive at this Z for every single image or for every single input. So you arrive at different parameters for every one of these. However, what we'll be doing, and that's sort of the mixture of now this old school inference with new school deep learning, is what's called the amortized inference technique, which is much more efficient. The amortized inference technique is quite simple. So what it means is we simply parameterize a function that goes from observations to the parameters of the approximate posterior. And we do this, of course, with a neural network. So instead of optimizing a set of free parameters, we simply have a neural network, which takes X as input and outputs, in the case of a Gaussian, the mu and sigma, which are the two parameters which control where the Gaussian is and how far it's spreading. That's what we get for Z. So the neural network is now shared by different observations, which is as standard as it gets for us deep learners. But the left-hand side, this memoryless inference, is what was the typical case for inference. So you need to keep that in mind. All right, this amortized inference is then what we'll do to get the individual parameters for each observation. So now these parameters that we will be learning, now instead of learning something for every input, we'll be saying that these phi, which gives us the variational parameters, represents the network weights now. This network which takes X and outputs this Z. And now, again, these are trained jointly with the model parameters theta to maximize this elbow. However, keep in mind that because amortized inference isn't perfect, because now this model needs to be working for all the possible inputs, we have a potential gap, basically. We have a potential delta that might yield suboptimal results. However, the benefits are pretty big. So the benefits is we don't need to learn variational parameters for every input, so it doesn't scale with the data set size. It's literally just the size of a network. and we only need to specify the parameters, and the rest gets learned. And for a new observation, all we need to do is a forward pass, and then we have an approximate posterior distribution over the latent variables at the constant cost of just one forward pass. Question?
I feel like I just want to understand this neural network aspect of this a bit more. So the input would be any instance of, say, an image or something, and then the output would be the mean and standard deviation of the
Posterior distribution, yeah. Yes.
But not necessarily of the data. I don't know.
It will be the configuration of Z for that particular image. Yeah, and that Z will then be used to reconstruct that image. That's how you train that Z, actually.
So it would be the, but then what is the distribution over? Like what is P or Z in this case? Like what is the output? Is it, it's supposed to be mu and sigma, but
so the question is what is the output of the distribution? You simply take a vector, a high dimensional vector in the Z space. You sample from it. And that's what you use then for reconstruction. But it might get clearer in a few slides, hopefully at least. So our objective is to maximize the elbow with regards to the model parameters theta and the variational parameters phi, which is non-convex. And we need to compute the gradients. And this is what we'll be doing in the next slide. But before that, and maybe that one already helps a bit, I want you to take just 3 minutes and discuss with your neighbor the following points. And perhaps you can mention what's the main idea, what's the difficult thing to understand here. First, generative models and Bayes rule. Second, Jensen's inequality. And third, inference versus variational inference and amortization. All right, 3 minutes. Have fun. And yeah, if you're not sitting next to one, maybe you can talk with your upper parts. All right, let's, if we moved seats, let's get back to our seat. All right, are there any new questions that have popped up? Yes?
This might just be me, but could you just go over the definition of amortization again? I feel like that's the one.
Right, amortization. The idea is that instead of, I mean, you could be having one neural network that gives you the Z per image. You could do that. It's a very weird thing to do, but that's kind of the thing that would be the traditional way to do inference. You learn variational parameters for every input, And again, if you're inferring over some physical system or something, this would be fairly natural, but we're talking about images. So the amortized inference now means you train it on a bunch of images and they all share the same process which gives you the Z. Yeah, in the back?
What is the lower bound for actually? What does the bound? I don't get that.
Okay, what is the lower bound? So what we're trying to get is this P of X, right? And we're sort of parameterizing it with theta. And the elbow simply lower bounds this thing that we want to end up with. So, and for example, if something is a lower bound, it means it's like always behind. But if this thing goes up, it means this thing, this thing that's being lower bounded also needs to go up. And this is sort of the thing that we started with, why we want generative models, right? P of X. Still, does someone else have a better explanation that might otherwise come to the front after the lecture? Maybe we'll have something. Oh yeah, was there someone? Yeah, go ahead.
I would explain maybe a lower bound as like the worst. We are like making the worst case better. So even if we hit the worst case, which is the lower bound, it will still be really good if our worst case is really close to our optimum.
Right, so a lower bound is the worst case that could happen, and as long as we improve the worst case, so that's here, the worst case, that one is still improving, so that's good. I mean, in fact, we might be quite close to where we are, but as long as we're improving the worst case, it's getting better, so that's the reason why improving a lower bound is something good.
So we have improved the lower bound.
Yes, yeah, exactly.
Optimizing the parameters.
Yes, exactly. We're improving the lower bound by optimizing the parameters, yes.
And the lower bound runs on function P of X, right?
Yes.
So by improving the lower bound, we are getting closer to P of X.
Yes, correct. Thanks. Another question? I think one there.
I have a question for the patient of the generative model.
Yeah?
I get that, yeah, although you said we used to do the discriminative models, now we go to generative models, but we have two types of generative models there. So was the point of this base rule that if we only need to calculate one of them to get the other?
The point here is shown, well, the point as it is depicted is you can arrive at something even like a conditional generative model by just having all the stuff that we already know plus an unconditional generative model, which is this P of X again. So, and this discriminative model we already have, the prior overlay label is trivial. So all we need to arrive, for example, to complete the picture at a conditional generative model is this unconditional generative model.
So our aim is the conditional one?
Not necessarily, no. So we do generative modeling for its own sake, but this just shows, okay, once you have that, you can do the rest as well. Yeah, yeah. Was there a question here as well? All right, thanks. All right, cool. So the slide before the quiz, or before the break, was basically this one. So we need to compute the gradients with regards to the elbow. So first we compute the gradients with regards to the model parameters, theta. And this is easy. So it's written out here. The expectation is independent of any theta, right? So you can literally put this grad, this triangle, this nabla operator, you can move it inside the expectation, so nothing fancy there. And again, the denominator only has phi, so it's independent of theta, so that's you don't care much about that one. And in the end, you get this approximation, and you still have this expectation, but you can simply approximate that now with a Monte Carlo estimate. And in fact, you simply generate one or more samples from this distribution and average the resulting gradients. So that way, you can train with regards to the model parameters quite easily. With regards to the variational parameters, we will face a difficulty. So now we do the same thing, but take the gradient with regards to phi. And already what we arrive here is we cannot now take the gradient operator inside the expectation, because now the expectation is over something that's dependent on this, on these variational parameters phi. So we don't know, I don't know, how to take gradients of an expectation, right? So that's sort of where we're stuck. So we need one last trick to make it all work. And this one last trick is called the reparameterization trick. There's another method called reinforce and likelihood ratio estimator. But we'll be talking about the reparameterization trick, which is super general, can be used in a couple of scenarios. However, mostly for continuous latent variables, for discrete ones, there needs to be some fixes, and works pretty well. So what is this reparameterization trick? Oh my God. So what we do is we reparameterize a sample which we need to take, because we are doing the expectation, so we need to sample, by expressing it as a function of a sample E from some very fixed distribution. So what does it mean? So we write now Z as some function G of epsilon given these variational parameters. Now, what we need is that this thing needs to be differentiable with regards to phi. Such that when we write it out, we can simply write, instead of having the expectation, well, this P of E, we can simply sample from P of epsilon. And then this epsilon will be independent of phi, right? Because it's simply epsilon, which is independent from fixed distribution. So now we could take the gradient inside of phi. And so how does it look in total? Oh, well, we can rewrite it with a chain rule. How does it look in total? We can, where is it? Here. We can write it as follows. So you simply sample epsilon from a normal distribution with mean 0 and identical covariance matrix, so just a diagonal one. And then you simply add a learned mu, and you multiply it by sigma. And that's how you arrive at this distribution. So your variational parameters simply scale and shift this random distribution, and that way you can have a distribution which maps this epsilon to z, but is differentiable with regards to the parameters of the distribution. So the parameters of the distribution, mu and sigma, right? They're differentiable. They simply get scaled with this epsilon parameter. Multiplying it by some random number means you can still compute gradients, right? So that's fine. However, because we multiply by this random sample epsilon, we now have an additional factor of noise. So that will be a bit of an issue. And yeah, so this mapping is importantly differentiable. So this might make it a bit clearer again. So always visualizing stuff generally helps me, is quite useful. So what we have, once we have a z, and then we do something with it, that part is no problem. We can do backprop. However, if we have some parameters like mu and sigma, sampling is not something that you can differentiate through, right? So but that's exactly what we try to do. So this reparameterization trick now simply does the sampling somewhere else from some trivial distribution, 0, 1, and then scales and shifts this distribution so that the resulting sample looks like it came from this distribution that we wanted to take from, but now you can have the gradients flow. So that's the main thing about the reparameterization trick. And yeah, so it looks like the following overall, basically. So you have your encoder network, which gives you this vector of means and vector of standard deviations for every latent dimension. And from that, you sample a latent vector. And the sampling is done in a manner that can backpropagate all the way throughout the whole network. Because otherwise, with the sampling operation, we wouldn't get any gradients. So where have we arrived? So cool bird, right? We can choose any simple parameterization of Q. but optimization requires a difficult gradient of an expectation involving the variational parameters that we wish to take gradients from. And the broader context here is that I've tried to make clear in the last slide. Sampling, it's just like taking a patch from an image that's not differentiable. So we can approximate it with a sample that carries the same mean and variation. And the key idea here is this reparameterization, to have a generic stochastic epsilon and learn the different scales and shifts. And that way we can have the gradients flow. So the VAE summary so far is that it's a generative model with continuous latent variables. That's the Z's. The likelihood and variational posterior are neural networks. And the prior, this P of Z, and the variational posterior are usually fully factorized Gaussians. So that was the fact that P of Z equals P of Zi times P of Zi plus 1, and so on. And the VAEs are trained using amortized variational inference. And we take advantage of the reparameterization trick. And put another way, and we can remind ourselves of the picture from the 10th slide or something, VAEs in a way are noise-regulated autoencoders, right? Like we have a very nice theory now how we arrive at this, and that we're doing variational inference and that we're optimizing an expected lower bound. But in a way, they are looking like noise-regulated autoencoders because we have noise in the middle. And this noise sort of constrains where the possible images lie in the Z space. And once we constrain that, it means we can sample from there because we now know the second Z dimension is not somewhere in space, but we know exactly where it is. And that makes us able to sample from it. So a final rewrite of the elbow in another way. The first term measures how well the model predicts. So that's the reconstruction error. And the second term is a regularization, which pushes the variational posterior towards the prior distribution and measures the amount of information that is conserved compared to the observation. And this is actually often computed analytically. Putting these pieces together now, and we're getting there. We're almost done here. We have the input data. We get from the encoder these mu and sigma vectors. Then we do this reparameterization trick and get this sample Z. Once we have the sample Z, we can reconstruct. Or here, actually, we get these mu's and sigma, and then the decoder generates a new sample. And we can vary this set in a couple of ways. So for example, if we have Z to be two-dimensional, we can simply vary it in some nice manner, just like you can, for example, here literally this is a grid which goes from -1 to 1 in both directions, and you sample a point from there. And now you send this through the decoder network, and now what you get as an output is simply depicted in that location. And now the question is, this looks, of course, very nice, but why does it seem to learn stuff that makes sense like this? And again, the reason here is this bottleneck. So in order to best reconstruct the data, it needs to best use the available space. And if we have two dimensions, these two latent dimensions will be best served when they capture the factors of variation that you see in the data. And the factors of variation that you see in the data is something like the tilting. For example, you often see ones that are like all kinds of digits which simply are differently tilted. So that's an important factor of variation in the data that's worth capturing, so that the network ends up capturing that one, for example. And of course, the other important factor of variation is the digit itself, which is, of course, sort of split in this whole 2D space. You can also see that the dimensionality is important. Actually, if you go towards very high dimensions like d equals 1,000, you will start having optimization issues, which, of course, this theory doesn't tell you anything about, right? So again, this is where theory meets engineering, and you need to be careful of that. A quick sort of thing to think about. when you do the next assignment or when you want to think more about this, is why these pictures that you typically see as outputs from the normal versions of VAEs, why they look blurry. And a hint is they're not blurry, they're actually noisy, and what you're showing is simply the averages. Right. Before we go into newer versions or applications of VAEs, we're going to go back to the suboptimality point that we had earlier. So we had these two points about having a variational posterior and the amortized inference, which both gave us these different gaps. And what we typically observe is that the true posterior, the main difference or the main difficulty is that the amortized inference is not good enough. And the approximating distribution is often fine. So like the Gaussian that we talked about, as long as you have a big enough network that transforms this in a nonlinear manner, that's typically fine. And the two approximation gaps, we can also write them out here. So one is that we already had, so this gap to the elbow, which is simply this KL divergence. So once we have a very good variational distribution, we can close this one. However, the second gap about the amortization, which simply means that we cannot get good enough variational parameters for a given image, is a bit trickier. You can also partially solve it with stronger networks, but yeah. So you have these two gaps, and this relates also to the fact that we have multiple factors of noise in our optimization procedure, right? We had the reparameterization trick noise that's coming in there, and we had the Markov, the Monte Carlo estimates, where we said, okay, instead of summing this up for k equals n or k equals infinite, we're simply taking the sum over a few. So this is also being, has a role to play in these ones. Right, so just a few VAE variants. So there's conditional VAEs. So you can quite easily construct, once you have the VAEs, you can quite easily construct them in a conditional manner by simply outputting them on some label y, for example. And you can also modulate them. Label y could be, for example, object segmentation mask, or they could be all kinds of, they could be the right-hand side of the image, could be the thing that you give it in addition, and you're trying to reconstruct the left-hand side of an image, for example. That makes, you can condition it on anything you want, really. Here you can see what the equation looks like. And the basic premise here is that now you're, in addition, you're giving this, and this is depicted in these square, in this square form with the real 3, basically. You additionally give the label as input, and you give it typically as a 1 hot vector. So just if it's 10 digits, it has a 1 where there's a 1, and if you're trying to encode the 3, it has a 1 where at the 3rd location, for example. And these are the sort of outputs. For example, in the top row, you either let it generate 3 quadrants or 2 quadrants from an input. And in the bottom row, for example, you simply give it as inputs the pixels that are depicted in the middle, so the blue line, and then you allow it to reconstruct everything that's not in the middle. And you can see that just by giving it the pixels in the middle row, it can reconstruct digits pretty nicely. Right, so these were pretty basic upgrades. Another really basic one is a beta VAE, which tries or has as its goal to get even more disentangled representations. So even more where if you go along one axis, you, for example, change the hair color. And then if you go in the other axis, you change the hair length if you're, for example, generating new faces. So these, the goal here, that's the goal. And the simple fix they propose is simply, we had this loss function, and they simply multiply the KL divergence with a parameter beta, which you then, of course, need to have some incorporate in your loss function. But this is essentially the main idea, to weigh this KL divergence higher. Right, and that makes it a bit more steerable. For example, yeah, you can see on the left-hand side on the top that if you change one dimension there, it sort of relates better to the camera angle or the pose, and similar for a direction like smile. All right, any questions here? The final thing, and that's sort of the technique that's being used for the stuff I showed earlier about the music generation in DALL-E V1, is called VQVAE, and there's a second version, VQVAE2. These are now pretty state-of-the-art, or especially the second version of it. Here the idea is that you do vector quantization, so you have essentially a more complicated bottleneck thing happening in the middle, and you have much stronger decoder networks, etc. But it's basically a more modern version of the VAE framework applied. And the VQVAE2 then does this in a hierarchical manner. So you do it for a small image, and then you do it for a larger image. And these multi-scale approaches typically work pretty well for images. And yeah, that's it for today's lecture. And next time we'll be talking about generative adversarial networks and diffusion models, and a bit about ethics about generative models. All right, thanks.